we should do it to have a class if you guys will attend. Okay, let's do a quick review. So multivariate Grasnov theorem, this is what we did last time. It's exactly in the same spirit as a single variate one. You can see that here, right? Now you have drifts in all the d directions. So these are your drifts here. And then you get a new change of measure where the old Brownian motion, uh, it's no longer the old Brownian motion, but old Brownian motion, if you add drift to it, then that's a Brownian motion. That's now a standard Brownian motion. Meaning the old Brownian motion now is new Brownian motion minus the drift. Okay, so this everybody kind of knows. So now we'll have a multidimensional market model. So we'll have M assets. We're going to assume that they depend upon D noises, right? B1 through BDT, these are Brownian motions. And first thing to observe is that we can write this in a similar fashion as we do for single asset. What we do is we define dWIT. Basically, we define a new process WIT as follows. Sigma IT is just this normalization term here, right? And then you can check that the WIT defined in this manner is going to be a Brownian motion. And that's because these guys are martingales. So WTI it's just a varied combination of martingales, linear combination of martingales. So it will also be a martingale, right? And then you can see it's continuous in T just by definition. And then one just has to check that the quadratic variation is dt, which indeed is by design true. So indeed WIT is a Brownian motion by Levy's theorem. That's right. That's exactly right. Yeah. So that allows us to write it in this manner: DSIT is AIT, SIT, DT. So it's not entirely, just a technical thing. People actually have different kind of, in Wall Street, banks will have different groups tracking different stocks. So they will tell you, okay, what the volatility of stock I is, what the drift of stock I is, right? So you get that data from them. You can fit to all this, and then you simply have to kind of get the correlation between the stocks, right? Okay, so we need now that we define this WIT and WKT, we need to find the correlation between them. These are mean zero variables, so we just need to find this expectation of the product. And that you can see will have this following representation. And typically sigma ij's are going to be constants, then all of this will simplify further. They will not be functions of t. So then this function simplifies function. And why does this happen? Well, you just kind of have to go back to applying Ito's lemma to WIT, WKT, right? These two are stochastic integrals. So when you take the expectation, they vanish. The quadratic variation term contributes this term here. And when you take the expectation, you get this covariance term. Okay, so we're back to the multi-dimensional market model. We have our risk-free security as before. We're just allowing R of t, small r of t, to be adapted process. So it's more general. Then we look at discounted securities, RT, DSIT, SIT, DRT. Then this the second order term. And SIT, of course, again is as follows as before. So now when you plug this in, you get that DRT SIT is given by the following formula, right? So discounted stock price as the following representation. And we are looking for a change of measure under which it's going to have, it's going to be a martingale. That's our objective. No, SIT is ith stock. So this is for I equal to 1 to M. Okay, remember we started from this model right here. Okay. All right. So we have this representation and we are asking ourselves, is there a change of measure under which this will be a martingale? And the way to get change of measure is through Grasnov's theorem. So what we can do is we can twist each Brownian motion in the following manner, right? We can add a drift to it, beta jt dt drift to it. That's what we can do for each of them. So then to make this into, to make this term vanish, we add a drift here in such a manner that it exactly matches this drift. It exactly cancels this. So that simply boils down to coming up with this beta j t, j equal to 1 to d, such that this relationship holds. Right? So existence of equivalent martingale measure boils down to finding beta j t, j equal to 1 to d, so that this process is a martingale that corresponds to, this beta g's will show up here as a negative term, right? And then they have to exactly cancel this. So we need these equations to hold for each t, for all t, for all omega. And all of this, when I say for all, I mean kind of almost surely, and for time, I mean almost everywhere. Right? So in other words, we need the solution to this vector equation, a bar t, a arrow t, let's call it, minus r arrow t is, and sigma tilde t now is a matrix. So this has to be true. Now I'm going to make a simplification, because typically it's true, one can do the analysis more generally, but typically we do assume that m is equal to d. So that the number of noise sources, number of Brownian motions equals the number of assets that you have. That's a common assumption. Let's assume that for now.
Just to be clear, this is like saying the market is complete in this case.
We'll work out when the market is complete, but this will certainly help. By itself, it's not enough.
Okay, this is on the line of saying you have M securities, like D securities, but now independence you have to worry about. When you try to draw analogs to the discrete time,
Yeah.
so M securities and you need them to be independent. You will not. If you have D outcomes, there's a
Yeah.
motion.
You're saying that in the discrete setting, we had two scenarios at every time period, so we need two securities. So then we got two.
We also talk about in general M securities. Then we need at least M securities.
Then that's right. So then from 2 we went to M scenarios and need M securities. But yeah, so that's so that you get a market to be complete. So it's in that spirit, yeah. So we do have D sources of noise, Brownian motions, yeah. What's that?
So why is it that how do you go? Why is one source of noise not enough? Like, because in some sense it's noise, right? So like,
So all the securities are being influenced by the same noise, then they'll be perfectly dependent in some sense, right? Yeah. Just by observing one security, I can infer all the other securities, which is not the real world. Yeah.
beta J is the drift associated with the chain Brownian.
That's right. Yeah. When we can twist it by beta J. We want to change the measure of each Brownian motion, so that under the resulting measure, all the discounted assets are martingales.
Sigma.
Hmm? Sigma is just this thing, right? It's the noise term here. It's ith security, each security I, sorry. So let's just go back to the model of ith security. Let's go further back, I guess. Sorry, it is very polluted here. So ith security is sensitive to jth source of noise, and sigma ijt is the sensitivity to it. The larger its value, the more sensitive you are at that time on that sample path. So this is kind of the underlying model of stock price. It's separately fitted.
So in that case, how do you know what the beta is?
Yeah. So let's just get this order very clear. Somehow you have lots of historical data. You come up with the best guess model for how the stock prices are going to evolve in the physical world. That's given by this model. That's your underlying model of how the stock prices are going to evolve.
That is the sigma.
That will involve knowing the sigmas and the AIs. No, I'll tell you. So I just want you to accept this fact that we looked at the past data, and now we believe in future the stock prices are going to follow this stochastic differential equation. That's a model for stochastic for the stock prices. That you agree, right? And we model dependence also here. So this is the underlying probability model. Now we are saying, is there another probability measure under which the discounted securities are martingales? And that's where the betas will come into play.
you mentioned like something to do with relations between
Well, right now, all I'm saying right now in this world, so these are all important questions. I was going fast because we had done this last time. Uh, when we created this model of M stock prices, they are moving in a correlated manner because they all depend upon same independent sources of noises, right? They just have different sensitivities to the same noises. Sigma ijt is a function of I as well as j. So they have different sensitivities, but the same noises. So that builds in correlation amongst them. So they move. So now we have to understand what that correlation is.
what do you understand?
Well, get an expression for it. Every correlation is a well-defined function. Yeah, yeah.
So then we're trying to get sigma. Okay. So like for sigma,
You don't look confused. You seem to be suggesting that, right?
sigma are the sensitivity, which are not the same as correlation.
Yeah, yeah. Correlation is going to be between expected value of SIT and SJT,
Right.
right? That would be a way to find the correlation.
And that would also depend on the data.
That will depend on all of these things, but it's not sigma IJT yet. I've just told you that this is how SIT evolves. So we have to figure out what that correlation is going to be.
And what's the motivation? Like why would we do that?
Yeah, it's a good question to ask at this stage of the course. We develop a model for stock prices, okay, so that we can, if we have options on them, we can price them. That's the motivation. We want to price options whose payoff depends on these underlying stock prices. We,
Like correlation between stock.
yeah,
How would that fit?
yeah.
Because
See, it all started with Adam and Eve. Yeah, let's go from there. But we have been doing this course. The point is we are going to price stock, we are going to price options which depend on multiple stocks. Okay, so you have a call option, not just on Tata Steel, but depends on Tata Steel and Larsen Tubro and Infosys and all the others. So then we need to have a model of how the stock prices of all of these different companies are going to evolve. Okay. Now it so happens that they evolve in a correlated manner. They go up together, they go down together. We build a realistic model which will have correlate them. We need to have a calculation of what the correlation is. So the way we build this model is we've said, okay, this IH stock. No, these are actually it's good to have this discussion now. This is just a way we've chosen to model things, right? We said that they're D-independent noise sources, D-independent Brownian motion, and stocks evolve in the following manner. Now that's a mathematical model. One question is how do we estimate these parameters so that we have a realistic model? And maybe we look at the past data in some way. We do a fit. But then we have a realistic probabilistic model of how all of these stocks are going to evolve. So they are going to evolve. They're going to evolve somewhat in a correlated manner. If this is the underlying model, what's the correlation? That needs to be calculated. Okay. So, all right. So then we said, okay, it helps us in doing this calculation by defining sigma t as follows. It's just a normalization constant. You have a question?
So, like, I guess when you're kind of see that process, is there any way to cross-validate whether or not the similarities are?
There, I mean, it's like in any kind of statistical fitting. So yeah, you look at the data, you have a hypothesis, you look at data, you do a testing of hypothesis to see if it's coming from there or not. Yes, yes. Mm, mm. So that's true. But right now on faith, we are saying that let's for now assume that we have a good model, right? So this is a reasonable model. And then by the way, nowadays it's very interesting. So this is how theory developed. Because in 70s, 80s, I think right up till maybe 5 years ago, 7 years ago, people believe that for stock prices or for many processes, you need to have a stochastic model. You fit a model first and then you develop things. Nowadays, we are coming to other view that maybe we can do things in a data-driven manner. We don't fit a model at all. Now, so we don't have to worry about all these things. But that's still just one way of doing it. There's enormous elegance and insight that comes from having a model.
something. So you have P, you want to P delta, you want to martingale, you
Yeah.
have this price that.
That's right. Yeah.
So where, so now how is, so P, the price does not depend on P at all. That's the
It does depend on P, but just not on the drift. Yeah.
the noise.
Yeah. Yeah. Yeah.
How do you get the price on balance? Big problem if you run.
I mean, as we've always said, price of the option in this world is going to be price of the replicating portfolio.
And that period coefficient matching.
And just that in the replicating, yeah, so how we construct a replicating portfolio, we'll do coefficient matching. And then we'll conclude that replicating portfolio's uh, value is best observed under a martingale measure, where all the securities are when discounted at martingales.
Is this coming from the convenience that,
Convenience.
so we first thought that we want option prices to be martingale.
Only for convenience.
No,
We want to, yeah, no, I'll just repeat what I've said a few times. We want to price an option. Price of an option is the price of a replicating portfolio. Now, what is the value of a replicating portfolio? That's best seen, that's conveniently seen under the martingale measure. So we look for a probability measure under which all the securities when discounted are martingales. The advantage of that is then the portfolio which comprises of using all of these securities is also martingale. And now price of a, because it's a martingale, its price, it follows these expectation values and that tells us that gives us an expectation representation of the price. So yeah, what's your question?
so the point that this method came from the idea that okay, it's good if it were martingale. So now we want to somehow remove the drift so that your stock loss is also discounted stock loss is also from the market.
That's right. That's
So
it.
does that-
That's exactly the thinking. Yeah. Okay, so yeah. No, it's very, yeah, I'm going very fast. So this was important to be clear. There's the underlying model, and now we are looking for a martingale just for computational convenience. And martingales are tools which help us do a lot of other analysis. Okay, so sigma IT was this normalizing factor. So we define a new process DWIT. Okay, for each I. And as we argued, we can show that this is going to be a Brownian motion too. Okay. So now we can replace this thing with sigma IT, WIT. So that is what we did here. So just a new representation, but we're saying exactly the same thing. Okay. So where this is standard Brownian motion. But now across I, these Brownian motions are correlated.
So, what do you mean by
Market will be?
being inconsiderate?
We'll come to that, I think, at the right time. Yeah. Abhi to, yeah, we'll have to get some basics in place. Okay, so far you're with me. And then the point is, okay, how are WITs correlated? So that I'll tell you how SITs are correlated. Anirban will ask you, hopefully, in the homework today. That's the question you can take from Shri, I guess. Yeah. Okay. But our tool in this, for any kind of analysis, is Ito's lemma, which is what we apply here. Okay. So now we are back here. Right. We want to kind of come up with a change of measure which makes the discounted process become a martingale. Right? Because that's going to help us do computation later. So then we write this, we come up with the representation of this D of RT SIT, the discounted process. And to understand this, we can use Ito's lemma. So it's RT DSIT, it's RT DSIT, SIT DRT, DSIT DRT. What's DSIT DRT? Zero, right? Because DRT has finite variation. So you get the following expression here. And again, we just go back and we say, okay, WIT was in any case just a placeholder for this quantity. So really what we have is this quantity right here. And now we have a clarity because the only changes of measure we can do is changing the Brownian motions. We can twist them. We can change their drifts by Gersdorff's theorem.
Just like say, only that's because this is
Yeah, no, I need to show you something. I need to show you that all changes of measure under the martingale representation theorem setting where the noise is coming only from Brownian motions,
Will that is just a noise?
only change, all change of measure will look like this. But let's take it for faith for now. For that, you'll probably have to come on Tuesday next week for the class. Okay. All right. ठीक है. So then we're looking at changes of measure of the following form. ठीक है. So and now we're hoping to choose our beta j's in such a manner that this process here becomes a martingale under that change of measure. Right? And that corresponds to just solving these equations. Right?
This we can only solve when d.
Well, we can easily solve when d is equal to m. Otherwise, we run into all kinds of dimensionality issues, linear dependence and all that kind of stuff. So we'll keep our life as simple, and that's also true in practice. We are going to assume that d is equal to m for now. You can read up, people generally spend more time doing linear algebra in a more general case where d is more than m. No, I mean, you have to make some special assumption on the parameters for the no arbitrage condition to hold. I mean, bounds you get if you have incomplete market. So right now, I'm just kind of trying to make sure that, I mean, before we talk about incompleteness and completeness, we need the existence of risk neutral measure. So right now, I'm talking about conditions under which risk neutral measure exists. Here, I'll argue quickly that if indeed these equations don't have a solution for all omega and for all t, they don't have a solution. That means for some omega and some t, they don't have a solution. Then you have arbitrage. So for no arbitrage implies this needs to have a solution. And in this case, what that means is for the solution to exist, you need your sigma t to be invertible. So then you can solve your beta tilde t right here. So that gives you a change of measure. So when you are fitting the model to data, if you want to get it's kind of fair to say that the no arbitrage principle holds in the world. Because if there was arbitrage in the world, what would happen? There are all these banks which have groups called arbitrageurs. they have already exploited it. So they made sure it doesn't hold. Huh. Okay. So for that reason, we might as well look for sigma t, which is invertible. So when we do the fitting process, we look for sigma t, which is invertible. Okay. All right. So it's very nice that how kind of theory and practice go very nicely together in this world. Okay. So then we have a martingale. So then this neutral measure exists. Okay. On the other hand, suppose this does not have a solution, right? Suppose your sigma t you fitted, assuming it's invertible, and then you did a testing of hypothesis and you found it's a very bad fit. So that's not a good idea at all. So only thing that matches data is some sigma tilde t, which is not invertible. So it doesn't have a solution. But in that case, you should try to make money. There's an arbitrage in the system. So now, just to, I guess, build up the argument, let's take S tilde t to be a diagonal matrix, where the first element is S1t, second element is S2t. So this guy not having a solution is same as this guy not having a solution. I mean, if you just write down the equations, all I've done is I've multiplied S1t to the first equation, both sides, S2t on both sides. So if one has a solution, second has a solution. Right? So I'm going to assume that this guy does not have a solution then. And then I'm going to construct an arbitrage. So that means there exists a theta t. So it doesn't have a solution basically in a positive set of t and omegas. Set of sort of positive measure of t and omegas. Okay. Then there exists an adapted theta t such that theta t in the null space of ST sigma t, right? It's perpendicular because what we are saying is that there's no linear combination of these guys which incorporates this vector, which includes this vector. The span does not include this vector. That means if theta t is in the null space, there is some theta t in the null space, which makes a non-zero angle with these guys. It makes a non-zero angle omega t by omega t. I can assume it's positive as follows. Depending on omega t, the above may be true as greater than or less than inequality. If it's always less than, then I can just reverse the sign and make it greater than always. Else, whenever less than holds, I can keep theta t to be 0. And so theta t is non-negative and positive with positive measure. Right? So if it's positive on a 0 measure, then I just take it's negative on a positive measure, I just make the negative into positive. If it's positive with a positive measure, negative with a positive measure, on the negative, I just make it 0 theta. So then I have a theta t which is positive on a positive measure. So I get this on a positive measure of t and omega, basically.
What is theta t?
Theta t is just, well, right now it's just a vector, right? This is just linear algebra right now.
Any vector.
It's a n-dimensional vector. It's a m-dimensional vector in this case.
I mean, just to be clear, you're saying sigma t is not invertible, hence, so now instead of sigma t, you're looking at ST sigma t. and
That's
you're
it.
saying this guy is not invertible, so hence it has a non-zero null space.
Yeah. Yeah.
For the right hand side, it's 0, left hand side, it's not 0. If it's not 0, you can always just reverse and make it positive.
Yeah. That's right. So I can, at the end of it, I can get theta t. So, basically, what we are saying is, if I tell you that, okay, what do I want to say? Y equal to AX does not have a solution, right? So there's no combination of columns of A which encompass Y. Y is not this. Then there's some theta such that theta transpose A is equal to 0, so it's in the null space of A. And theta transpose Y is greater than 0. Theta transpose Y is either negative or positive. I take minus theta, then I get positive. Yeah.
This should be the right. What we saying first take transpose and transpose again. Because you just take a vector of like ST sigma t applied to zero. Without you take transpose first and transpose again. Is that
Doesn't matter. Yeah.
no, because it's a matrix in a vector, right? Not a zero.
No, ST sigma T
It's
is
a matrix.
But it's effectively inner product for each column of the.
Oh, sigma.
Sigma t is a matrix, right? Sigma t is a matrix. ST.
sorry.
So A is also a matrix, right?
No, I agree. Okay, so okay, just to be clear, but then you said okay, you took transpose, then that is also not invertible in the plan.
I mean,
Why did you left multiply? That's what I'm asking. Usually that just means that exists. If A is not invertible, then exists X so that AX equals 0. So now you're saying A is not invertible, so your transpose is not invertible.
yeah, I'm assuming ST sigma t is not invertible, right?
Yes, then because that is not invertible, for the transpose, that is also not invertible.
Uh,
It exists. Is that why you it doesn't left?
uh, so this is my A, and I'm looking at theta transpose A, right? And that's equal to 0.
So
That's
theta
what this.
transpose is a horizontal row vector, which each component is the inner
Yeah.
product of theta and that column of it.
It's just a row vector, but it's still all 0, huh? Yeah. So yeah, that's why. I mean, I could have written A transpose theta. Yeah, and that nothing changes there. ठीक है. And because it's for each omega t, so I have to worry about signs being different for different omega t. So then I kind of play around and ensure that theta transpose that I'm coming up with this, this multiplication results in a positive quantity on a set of positive measure. Okay, so once I have that, Now I'll use this theta because I'm getting this theta for every omega and every t. Yeah? And it's an adapted process because it just depends upon adapted variables. ST, sigma t, everything is adapted. Right? Everything here is adapted. So this theta t is also adapted. That's important because I'm going to use this theta t to construct a strategy. I mean, it's not like I'm looking in the future. Theta t just depends on these guys. That will help me construct a portfolio. Yeah, yeah. So now that I've got this, so again, I have this model here, right, of my discounted stock prices. What I'll do is, let's consider security M+1 as the risk-free security. Remember earlier we had the risk-free security and a risky security. Now we have M risky security, so M+1 risky and then one risk-free security. For a self-financing portfolio, we had earlier argued, because the portfolio is self-financing, D of the overall portfolio value is summation theta ti into D of RT SIT. So the same argument I'm going to use here. Theta ti again are just number of IH security that I'm purchasing. Okay. The only thing I'm not keeping here is I'm not keeping the M plus first term here. And that's because D of RT SM plus 1T. SM plus 1T is just the money market. So RT into SM plus 1T is equal to a constant. D of that is 0. So this relationship is true. And now I'll just argue that this portfolio that I've constructed gives me arbitrage. So I come back here. I look at this portfolio that I've constructed. Right? Basically, what have I done? I've chosen my theta in such a way that all my noise cancels. Right? That's a big thing here. All my noise is canceling here. Okay. So this is canceling and my drift is positive. The drift of the discounted portfolio is positive. Right? So the undiscounted portfolio, I've not shown the step, will have a drift greater than RT. So undiscounted portfolio without any risk has a drift greater than risk-free security. I can buy risk-free security and sell that one and I have arbitrage. I buy low and sell high and I have an arbitrage. So I've constructed a portfolio which gives me an arbitrage. By the way, this is cool stuff. One can actually implement these things to look for arbitrage in the market and do trading on it. So in this sense, when you say, what does Renaissance fund do and all these funds do, they do apply all of these kind of linear algebra techniques to look for arbitrages. And they are dealing with complicated products. Like,
We're getting this arbitrage because choice of theta will.
yeah. And theta t I got from the linear algebra thing because I could not invert the matrix. Because the market was not showing like it was, the sigma was invertible. So market was suggesting that there's an arbitrage. So then I could find that in this manner.
Also, we have theta t, which is our M.
Yeah.
Which is some portfolio. And we choose the M+1 coordinate such that, like, I don't understand how we choose the M+1 coordinate to allocate to the risk.
Yeah, so I didn't quite give the details here, but the point is M plus first coordinate is just the risk-free security. And when I change my portfolio in time delta t, I change my risk-free amount investment in such a way that I have a self-financing portfolio.
Okay.
I'm
we
not
aren't
putting
going-
anything, I'm not taking anything away from them.
Okay.
You have it, you had your phone on? Okay.
So
Yeah.
basically, there is no maximizer for the market.
There is a unique maximizer.
Can you find the
Possibly, I think that requires more work. Yeah, that's a good point. If indeed there's an arbitrage, can we find kind of maximum arbitrage? Yeah. Yeah, you can do these as projects. These are nice projects, yeah. But you can see, like all these prices make sense because, they're justified by trading. So that's why if you see an arbitrage opportunity, barring the fact that, okay, the model itself is kind of flaky, you don't really have a great fit of a model, and there are all these transaction costs, And when you buy and sell things, you impact the market. So you have to worry about all those things. So that's why you look for a substantial arbitrage opportunity. And then at least there's something there for you. All right. So where are we now? Yeah, so we have an arbitrage then. So risk neutral measure exists if, so it's necessary that these guys have a solution for the risk neutral measure to exist. And indeed, if they have a solution, if sigma t is invertible, then so it's if and only, yeah. So then risk neutral, at least when m is equal to d. Well, I guess all you need is that these equations have a solution. A sufficient condition is that sigma t is invertible. Okay. All right, so let's assume that for now. Let's assume sigma t is invertible. Let's assume that these guys at least have a solution. Then we have this relationship, right? Then our discounted portfolio is indeed a martingale, right? And we've identified the beta j's from here. So we've identified the change of measure where we get all these nice properties. Okay, so why am I repeating myself here? Yeah, now I'm talking about the portfolio process. So up till now, we were just saying that all these discounted securities are martingales. Now we want to say that the portfolio, a self-financing portfolio is also a martingale, which come under this change of measure. So self-financing portfolio process XT, its DXT is going to be just changes that happen because of the stock market, because of the underlying assets. Alpha IT is what's it's investing in the IH security. And the remaining money that it has, it's investing in the risk-free rate. So this is how the self-financing portfolio process is going to evolve. Right? Okay, now we just simplify this. We want to show that this is going to be a martingale. That's what we want to show. Under the right change of measure that we've already found out. So this we can rewrite. So we'll look at not dxt, but drtxt. And that's this rt dxt plus xt drt, right?
DRT XT will be
rt dxt. Yeah, we want to show that's a martingale. So this you have to do some calculations to go from here to here. But you find that this is going to be true. And it's kind of intuitive that the change is happening because of the risky securities. And alpha IT is the is the proportionality here. So this turns out to be true, which because we understand what DRT SIT is, plug that in here, we get that discounted portfolio process is also a martingale. It's also a stochastic integral. Okay. Yeah.
I have two questions. Firstly, we've uh, said that all these processes in the portfolio processes are adapted. But we need them to be predictable in a sense, right? I mean, it's not like I didn't look at it. Is there like a big difference there, or is adapted close enough to predictable and continuous?
I mean, when things are continuous, then they're the same. Otherwise, one has to be careful. Yeah.
And second thing is we assume that there's some m plus one with risk-free security. If we just assume m plus one security is it is strictly positive price process.
Yeah, you can generalize. Yeah, that's true.
So just to make a continuous case was when you have jumps that will be equal, but
Yeah.
here if you're predictable,
Yeah.
you have to make this continuity of price, right?
That's right. Yeah. Yeah. Here we adaptability and predictability go together.
Here, what was predictable?
What's that?
FT measure was FT minus. Okay. Okay, I need to continue a second.
Yeah. Yeah. I think that's correct. We're on track. Okay. So under P tilde, discounted self-financing portfolio process is a martingale. So that's where we are right now. As before, we can see that under risk neutral measure. And now the other result is that when the risk neutral measure exists, then you don't have an arbitrage. Right? So we said, okay, if there's an what did we say? We said that, okay, if sigma t was not invertible, then there was an arbitrage. So if there's no arbitrage, then sigma t is invertible, right? And then risk neutral measure exists. Now we're saying when risk neutral measure exists, there's no arbitrage, right? So to see that, so suppose we have a portfolio process. So arbitrage is how, let's define arbitrage. It's a portfolio process which starts with zero wealth. So and I think let's call it a self-financing portfolio process. Huh? So you can write that down in your notes. It's a typo. For some, and then at time big T, you have non-negative wealth with probability 1 and positive wealth with positive probability. Okay. Now this also implies that the discounted process has the same property. RT is strictly positive. This implies that if this quantity is 0, then this quantity must be positive, right? So if indeed risk neutral measure exists, then this cannot happen. So arbitrage cannot happen. Because under risk neutral measure, the self-financing portfolios are martingales. So we need self-financing here. Okay.
But if each security is a martingale, discounted security, even if the portfolio is not self-financing, it can be a martingale. It is a combination of security. So I've asked that Rob mentioned that you need self-financing to be martingale, but any portfolio is a combination of martingales.
No, there's this element of risk-free security also that you're using to, I guess, make the process self-financing.
Okay.
So your portfolio also has that part of that in part of it.
But question is still.
Yeah, that's true.
I was thinking it's probably the correlation. That's what they opted for.
No, I think his point is valid that if I start with a zero portfolio, and whichever way I play around with it, I can't end up with a portfolio which makes. Yeah. I mean, implicitly I'm saying that, okay, I can't really add or subtract money when I'm doing this. Right. So that's what the self-financing portfolio does.
Right. So if you start with 0, you are going to be in a.
Yeah. I mean, so let's just
Like what you're saying is by that, by the word self-financing, is you're not adding more money from your side.
You're not adding or subtracting any money. That's right. Yeah.
It could be 1 also. It doesn't have to be 0.
Right. So I think, yeah, so we are saying the same thing because you're also saying that if I just combine these guys and I don't add or subtract any money, yeah, then it remains a martingale. So the same thing is being said.
Self-financing is just matching the options price. Pay. That's all this.
That's self-replicating.
I mean, self-financing is just that not adding and subtracting anything. Yeah. So I'm going to change my portfolio, but in my changing my portfolio, I'm also changing the investment in the risk-free security. But I mean, discounted risk-free security is also a martingale. So I mean, your point remains that all of this is, it's just a portfolio process. Portfolio process where I'm not adding or subtracting anything. It's just being pedantic. Okay. So now the question is, so now that we understand that risk neutral measure implies no arbitrage, and no arbitrage implies risk neutral measure. Again, we are kind of brushing over technicalities that we will do. But to the first order, we have everything going correctly. So when can an option be attained? When can we price an option? So that still needs to be answered, right? We've talked that the replicating portfolio is going to be a martingale, but when can we construct a replicating portfolio for a given option? That still remains a question that needs to be answered. Okay. So we want to, yeah.
Is the portfolio process.
Yeah.
That is marketing.
Discounted, yeah.
So, yeah, arbitrage process. but why can't another process be an arbitrage?
Uh,
You should know arbitrage also that it's not just any such thing.
we've just defined that to be the definition of arbitrage. That any self-financing portfolio process can't make money.
We showed was that
So what else would you think would make, what else could be something which gives you money for nothing? Because I guess my point is one can always map it to this.
key this portfolio process that we treated earlier, you showed in the market.
Yeah,
If you have any other replicating portfolio, you can always be.
that's right. I mean, this is all self-replicating, any self-replicating portfolio process, right?
Yeah.
Yeah.
You not introduce.
So it is the, yeah, it is a very reasonable definition of arbitrage. Now you start with zero value. Now you could say I start with 50 rupees and I make 75 rupees. That's also an arbitrage. But I can, without loss of generality, just subtract 50 rupees from all of this. And then I go down to my definition. Or you can say I have some random positive money and I end up with random, yeah, same thing. Yeah, yeah, sure. See, now these slides are with you, right?
I think, yeah. No, these ones are, yeah.
This is there, I think, yeah. Should have come last night, yeah.
This lead time setting when we're talking about like portfolio data, we talk of state price.
Yeah. Right now, I won't come to that. I mean, I could bring them in as well. Yeah.
Also, bro, just for it, self-financing means that after time zero, I don't handle with it, or it has to be that it's zero. No, you can always.
After time zero,
So at time zero, I can start with anything, but after that, I'm not adding.
I'm not adding, subtracting money, basically.
At time zero, I can start off with, let's say, $1,000.
That's fine. Yeah, just, yeah, without loss of generality. Yeah. Yeah. Okay, so we want to now price this guy. Option is just a random variable, right? At time big T. It's measurable 0 FT. So since, and I'm going to assume now that the risk neutral measure does exist. I live in that world where there's no arbitrage and hence risk neutral measure does exist. Okay? Yeah. So in that world, I can compute this quantity, VT. T is just the conditional expectation. So in particular, RT, VT, with this definition of VT is going to be a martingale, right? So risk neutral measure exists. I know V of big T, I can construct this martingale process. So I'm going exactly as I meant in the single dimension setting. So I'll use multi-dimensional martingale representation theorem. And it's one of those nice words where it's an exact straightforward extension of the single dimensional multi-dimensional martingale representation theorem. Basically, there exists adapted processes gamma j_t. So that any martingale looks like a stochastic integral, right? With respect to all the d Brownian motions. Okay. So I get this for free. Martingale representation theorem has given this to me. My question again is, I've given this option. I want to construct a replicating portfolio process which matches this option. And martingale representation theorem has given me this representation, which I can try and exploit. Okay. All right, so what am I going to do? So I'll first just rewrite this in the following manner. Just shorter notation. Nothing has changed. It's the same thing as here. R0 is just equal to 1, right? Okay. And portfolio process, any portfolio process, self-financing portfolio looks as follows. Okay, we just saw that. So we want to construct a portfolio process which matches the option. Basically, we'll try to match the coefficients for each time and each. Okay. So I'll start with x0 equal to v0. And I'll choose my alpha ITs, which is what I can choose in my replicating portfolio process, right? So that this equation holds for each t for each sample path. Okay. RT I can just bring on this side. It's just a scalar, positive scalar. So I'm looking to solve RT inverse gamma hat T, gamma arrow T is sigma T inverse alpha hat T S hat T. With this time, I've just written it as follows. This is just notation for this. This is the old alpha T times the matrix ST, but yeah. ठीक है?
This is scalar, right? So that inverse is
Yeah, yeah, yeah. ठीक है. So I want to find alpha T. So I can find it if sigma T transpose is invertible, right? And I can find it for every option price process. Every option I can price if sigma T inverse is invertible, if sigma T is invertible, right? So for the market to be complete, I should be able to replicate each and every option. So a necessary condition is that sigma T should be invertible. And once it's invertible, then indeed I can solve for alpha T here. So that's also a sufficient condition for the market to be complete.
Well, sorry, could you go up with? Yeah.
why is this necessary?
Well, if it was not invertible, then I can find some option that I cannot price.
Yeah.
So it's necessary. And
you
if
can go to-
if it is invertible, then I can, yeah. Yeah. Right. ठीक है, so it's kind of, yeah. Alpha T was, oh no, yeah, bad notation. Alpha T is in our portfolio process. How much are we investing in each security? Remember, we created this replicating portfolio right here. So bad notation, that old alpha T has to go. Yeah, now it makes sense, right?
No, I might have missed this discussion if it happened online. But what
Everything happened online is being repeated. So
what if having is not equal to?
no, then I'm not discussing that case.
Because in reality, like we won't have any.
Typically, it will be. Typically, it's assumed to be. And you fit processes.
You see the number of scenarios that we said, right?
The number of securities I have
And the
and the number of noise sources I assume are equal. Yeah.
okay, that's fair.
It's a fair assumption, yeah. It's I mean, you could say, okay, I have 3 securities and 4 sources for noise. So then there's a lot of redundancy, yeah.
We did the same one. Every stock carries
Its own special extra noise, yeah. So it's a very typical assumption to make. Yeah. But you can do linear algebra more generally. I'm just not doing it.
Just this invertibility.
Yeah. Yeah. So you have more nuanced statements. All right. So then the market is complete and every option VT can be attained and priced. Recall that EMM exists only if, so equivalent martingale measure exists only if this guy has a solution. So now market is complete if sigma T is invertible, which implies this neutral measure also exists. So it all kind of boils down to sigma T being invertible. If sigma T is invertible, then you have a neutral measure and then your market is also complete. So it's a very happy ending here. So when you make nice assumptions, you live in a nice world.
So this is for the logical option.
Yeah, yeah.
Logical option yeah, stop it.
Yeah, yeah.
How is that? We can't do those backward engineering.
Yeah. I mean, this question would have also been a good question to ask when we were discussing the discrete time setting, right? Yeah, yeah, because I kind of thought of it, but I didn't keep it in the lecture. But the point is, all of this theory is about European options, where you exercise, you don't have the option to exercise early. You exercise at the final time, right? American options have this extra feature that you have to decide when to exercise, right? So then what happens? So we will discuss, hopefully we'll get time within the next 2 lectures to discuss Monte Carlo methodology, how people actually do that in practice. They use machine learning kind of ideas. But in the discrete setting, what it would mean is At this time, I can still price the option. If I say, this is my final time, I know my payoff is going to be so much here, so much here. I can replicate the option and say that if I don't exercise the option at this point, I know what the option price is going to be. Are you with me on this? I'm going back a bit. Yeah. So then I ask myself, if I continue with this option at this time, my value of the option is CST. But I know that I can exercise the option at this time as well. So and then I get GST, let's say. I take the maximum of these two. That gives me the value of the option at this point. Similarly, I get the value of the option at this point. Right? Then I say, okay, I know the option value here and here. I come to this point here, and I ask myself, what portfolio do I need to hold to replicate this payoff, these two payoffs here? Right? Basically, I'm constructing a portfolio to replicate payoffs. So then I say to myself, if I hold the option here, so this was at time 2, then I know at time 1 what the option price is going to be if I hold the option here. And I compare that with G1 S1 and tells me what the American option price here is going to be. So it's this backward induction that I do that helps me build upon the theory of option pricing. On top of that, I kind of do this control problem. So we didn't do this properly, but now you can see in the binomial tree how you would solve it going backwards. Yeah. Right. That's right, yeah. So now we'll look at this problem if we get time in the continuous setting and tell you how successfully this was a lot of work done using, because Monte Carlo simulation can use to price options in continuous setting, because after all this theory we get this representation of the option price as an expectation of a payoff under risk neutral measure. So you come up with the risk neutral measure, then you can use Monte Carlo theory, which was very popular. But then how do you use Monte Carlo to solve this dynamic programming feature where you decide when to exercise? So there was very nice kind of combination of early machine learning and dynamic programming to price these options. So there were very good papers that came out in late 90s, late 1900s, I guess, just before 2000s. We'll try to talk about that. That's how at least people of us who do applied probability got into finance. We thought we could say something. So I remember working on this quite a bit. Okay. Yeah, so this we've done. Let's move on now to the next one. How much time do we have? Okay, we have 20 minutes, 22 minutes, right? So interest rate models, but I think we'll probably just cover the initial part. So let me give you a version of Feynman-Clark formula. It's not the most general version. The most general version is not much harder than what I'm showing you. But suppose we have a SDE, right? Stochastic differential equation. We've been playing with these things. Again, what's nice about stochastic differential equation is that they're Markov processes. If I tell you the value of the stochastic of this SDE at time xt, at time small t, I tell you it's x of t, then the future doesn't depend on the past. It only depends on x of t. And again, the way to think about this is, you have this Monte Carlo model in your mind that I can generate x t plus delta minus xt is roughly equal to mu t xt into delta plus square root of delta sigma t xt into normal 0, 1, right? Right. Through this, I can start with x0, construct x delta, construct x2 delta, x3 delta. I can construct the whole sample path. At time t, I observe the Monte Carlo, this x big T. I can see what my option price looks like. I can do this again and again, take the average, and that becomes a procedure Monte Carlo method for pricing options. Yeah.
Just, like, we could do this concept.
We had defined it actually, yeah. I mean, you have to be more careful in how you define it, right? So you say, okay, expected value of any function, any Borel function x of t given f of t is equal to some Borel function g x of t. Okay. So that's how we define. For every h and g, this should be true. For every h, some g should exist. For every small t and big T. But the point is, in the continuous space, it becomes difficult to capture intuition. But really, what we are saying is, intuitively, it's very clear. Okay. So now, in the same spirit, I'm going to now define GTX.
We said that all these STs are Markov.
Are Markov processes. Yeah.
We saw that stochastic integrals are also STs.
They can be more general. Stochastic integrals allow for adapted processes, right?
Oh, SDs mean okay.
SD made this. See this mu t xt is a deterministic function of t and xt. Now
Say mu is always 0.
Huh.
Then xt equals to sigma t xt dvt.
Yeah.
This
So this is sigma is a deterministic function of t and xt here. That's a special structure. If I kept any sigma t here, which is an adapted process, for example, it can be a function of all of x of s, 0 less than equal to s less than equal to t. So I can allow those integrals, but then I won't have an SD. So SD is a very special structure of a Ito process.
Yeah, no, because
That's very important to be clear on. Huh? People usually spend much more time on these things in a stochastic calculus course. Huh?
all Martin is a Markov, but this is also
Yeah. Yeah, so this was important. Okay, but now let's start with this quantity, GTX, which is just basically I'll start my SD at time small t with xt equal to x. So this is my initial condition. And now I run the stochastic differential equation until time x of t. And I find g of x of t. And I take, it's a random variable. I take its expectation. That expectation I'm calling as small g of t of small x. Okay? Is this clear what's being done? I have this SD, which is basically a recipe that I can start at any time at any state, and it will give me a process, probabilistic process after that, stochastic process. Okay. The result, which is technical, kind of obvious intuitively, but really to show it's technical, it's it requires a lot of work. I mean, it's not just using standard machinery anymore. That is, if we start the SD at time t from state x, GTX denotes the expectation of generated sample GXT. Can show that conditional expectation, which is a random variable, right? Which is FT measurable random variable, is given by this GTXT. So not only is, XT a Markov process, so it has something like this, but this G is identifiable. So it's given by this term over here. Okay? So you accept it, right? It's very acceptable, this thing. All right. So now the point is this.
Oh, okay. So what does that expectation TX notation mean? That just means what you predict in this army.
Yeah. It's just it's a start initial condition I've given. Yeah.
You saying that exactly
The conditional expectation. It's a random variable which integrates like g of xt on all subsets in the sigma algebra f of small t. That's what conditional expectation means, right?
this is what the final.
No. So we're getting there. So this is true. Right? But now you know the way we define GTXT. Do you agree that's a martingale?
Sorry,
This GTXT, the way we define this, it's a martingale because it's a conditional expectation of single random variable. So this martingale will have a Ito's representation, right? But because it's a martingale, the drift term should be 0. So let's do that calculation. Yeah.
between GT and TXT, where is that XT?
Uh, what's your question?
G T and XT, right?
Yeah.
Where is small t being?
It defines a position.
No, but that small t is defined.
So capital T is how you define it.
I mean, this conditional expectation will depend upon small t also, right?
No, so my point is, these are okay. XT is a solution to this SD.
Yeah.
And now, like as you do, then you get some function. You get some random variable GX.
GTXT, yeah.
This start GX.
Capital.
Oh, yeah, big G. That's
XT is
big,
the solution to XT.
big GXT, yeah. So this conditional expectation will depend also on the time t, right?
What about XT? Where is that?
Um, where, why would X big T or X small t?
X small t. G is okay. Small g
Yeah,
function of small t and X small t.
yeah.
Where is X small t being used?
Well, I mean, just imagine how we are thinking about this guy, right? It's like you start with t and small xt, X small t, and generate a sample path till X of big T.
For them.
And I'm just saying this is what this, it's equal to this quantity. FT as such is just FT measurable, right?
So my point is, no matter what XT I choose, I'll always get the same output. So that's the difference, right?
No, no,
What small XT I choose.
no, you get different output, right? That's the whole point of all this. Your starting condition of the SD.
Look at the first. Okay, let's look at point number 2.
Yeah.
Over there, you can understand. If you start from a different state, of course, it will generate a different output.
Matlab, this guy here is just some Borel function which is FT measurable. So it could include X of T.
But from
And it,
No, exactly, but X of t is not in the notation.
well, I mean, the point is the way to think about this guy is it's the conditional expectation, right? Given all the information I have till time t, what's the conditional expectation of g of X of T? So this conditional expectation depends upon what X small X of T, X of small t happens to be.
I see. So you're saying that if I pick a particular XT, I can have more information on time t than with a different X.
Well, yeah, I have different information. Huh?
Like, it can realize different solutions, right? Like you might have F small t with XT, and XT can be different.
I mean, first of all, do you agree that, let me just put it this way. Oh man, sorry, I'm just. Do you agree that this guy is a function, some function of T and XT? Because it's a Markov process.
Okay, small question. What is G? Capital G is, which is like equal to X of capital G.
Yeah, yeah.
G sum.
Some option price, yeah.
XT is the underlying thing.
That's right. Yes,
XT is the generated, is the solution.
yes.
G of XT is just another random variable.
Okay.
So I understand that first definition, small g.
Yeah.
But
No, but what's the problem with the second definition? Yeah.
where is the second input of the variable being used, or the function being used?
Where is the second?
The question
I don't like this. I don't like this. Views to that.
And the question he's asking is why is the left hand side a function of t and x?
That's a good question. Yeah. So first of all, I'm just saying that's how we define Markov property, right? That's the whole point, that the future depends on T as well as XT.
Yeah.
So any conditional expectation depends only on T and XT.
We can think of it as G of F of small t. If you want to.
Meaning, I've observed the system till time T. F of T, the information that I have. Yeah. What that really means is that on different omegas, I have different information. All I need to know is, well, T and X of T. That's all I need to know the future value.
But the where is X of t on the left hand side? That's all I'm asking.
Well, this G of X of T, because, if my X of T is here, then I get a different X of big T. If my X of T is smaller value here, then I get a different.
FT is the filtration from 0 to t.
Yeah.
Is the sigma that was generated by XT.
Well, it includes that. It's certainly all the XTs up till that point are measurable with respect to F of T.
No, I agree it includes that, but do we say it's exactly that?
No, it need not be exactly that. It's more general.
So if it's more general, what is the left hand side? How we use the definition?
You don't use the word use.
Okay, so X
I do.
capital T is defined as a solution. Is that how we are small t you get
Mm.
by going from X small t and simulating it?
Yeah,
That's how we
yeah.
It's but then that's the first definition, right?
That's the first definition. All I'm saying is this, in the Markov, this is a definition, this is equal to this for some F. And now we are saying that F is exactly this small g here, where g has this nice interpretation. So it's a very intuitive concept. What's your conditional expectation at time small t? It's as if you start at that time small t at X of t, whatever that value is at that point, and just generate an independent SDE from there. That's the conditional expectation. This is, it's what you expect it to be, right? So what you're kind of confusing is, okay, why is x of small t coming in? And somehow,
I see why it's coming in, and you have some point, but why the left hand side is not, the second formula does not seem to reflect that. That's what I'm saying. FT contains that.
FT is, yeah, I mean,
It can also contain another XT.
Then Markov will make us forget that.
when it contains all that means is on every omega, it depends on these things, right? It's so for example, if f of t is exactly sigma of by sigma I mean sigma algebra of x of s, sorry, 0 less than equal to s less than equal to t, right? So this is the information I have, right? So every omega, this is what I know. And now future will depend upon this information. Because it's Markov, it will only depend upon x of small t. So that's what I'm saying, that this guy here depends on small x of small t. And this is just crystallizing in what way do I depend on x of small t.
FT is sigma algebra that contains
All this information, and on every omega, it's telling you something, It's telling you all the random variables that constitute f of t, for example.
XT also is necessarily random.
Yeah.
I mean, XT by definition has DBT. DXT.
So your problem is interpreting this guy. Yeah. It's something which is FT measurable. Yeah. So it could be a function of all the random variables that compose FT. But because it's Markov, it's a function of x of t. But it does depend on x of t. It's not like it's constant across x of t. It's not that. Yeah. Okay, but let's move on really fast because I'm going to make you stay another 5 minutes. You can separately deal with Rushil when you go outside the class. Okay. So GT, do you agree is a martingale? By this definition? And it's a Ito's process, so it will have a Ito representation. It's a function of T and XT. XT is a Ito's process. So let's apply Ito's lemma to it. So we get d of g is gt dt, gx dxt, and half gxx x dxt dxt. Right, let's open this up. And I've now added the arguments. So gt tx plus mu t. So mu t is right. Yeah, I've got mu t here. Okay, good. Mu tx gx tx plus half sigma squared tx dxx tx. I should have xt here, but since it's true for all xt, I've just kept x. I want this to be true for all x. Anyway, what I'm saying is, let me just, because I'm jumping a bit, I changed this order of slides, and that's why I didn't explain this one. The point is, I'm going to now find the Ito's representation, and I'm going to set the dt term equal to 0. Because it's a martingale, the dt term should be 0. Martingale does not have a drift term in it. Martingale is a stochastic integral. It doesn't have a drift term in it. So I'm just going to identify the dt term. And then instead of having xt in that dt term, because it has to be true for all xt, I'm replacing it by small x and saying that it's true for all small x. So I basically get this partial differential equation.
DT is 0.
The coefficient next to dt.
GT is 0.
The drift next to dt is 0. The drift next to dt is coming from gt is with there. This guy will give a term, and this guy will give a term. All of them give. So that's GTTX, mu TX, GXTX, and half sigma squared GXX TX. And this will have to be 0 for all small x. And that's your Feynman-Kalk formula. It's saying that this conditional expectation term that you have right here satisfies a partial differential equation. So just like some of you have seen Fokker-Planck equation, like people who are studying diffusion, then the density function of the SDE satisfies a partial differential equation. This is saying that the conditional expectations also satisfy a partial differential equation. This is the Feynman-Kalk formula. this conditional expectation,
Because it's a martingale. We use for martingale representation.
so that helps us arrive at that conclusion. But what we want to say is that this quantity here satisfies a partial differential equation. You can imagine in your mind a conditional expectation of a finite discrete time Markov chain. Right? What will expected value of g of xt be given that xt is equal to I? Now your t is taking discretely many values, x takes discretely many values. Then you can imagine this will satisfy a one-step equation. I can express this in terms of, if I knew these expectations at time t plus 1, I can write a one-step equation and expect the expectation at time, conditional time small t, in terms of conditional expectation at time t plus 1. So you get these one-step equations. If you've done Markov chain, you see these one-step equations all the time. If you've not done it, then it's a... So then this is a kind of a continuous kind of version of that.
This is sort of the backward engineering for the discrete case of
That's exactly right, yeah. And that Fokker-Planck is the forward case that you do. These are exactly your Kolmogorov forward and backward equations. Yeah. These are versions of that. But the point is, in some sense, you are looking for a PD when I give you a Markov process, because in discrete time, you have these forward equations and backward equations that Markov process satisfy. So you're asking yourself, what's the continuous version of it? That has to be a PD. So forward turns out to be Fokker-Planck equation, backward turns out to be Feynman-Planck formula. Just that it's much more generality, so one needs to kind of work hard at identifying the right formula. Okay, so now coming back to Rushil, your point, so GTXT is a martingale. So now how do we come up with the PD? Then the drift is going to be 0. That's exactly what we done. So that's a tool for finding out how to find these PDs. Okay. So this is Feynman-Cox formula. You can apply this tool more generally, and Feynman-Cox formula in that sense is more general. But let's carry on a little bit. So in options pricing, we don't just consider expectation of GXT. Yeah. Yeah. I mean, it's just a function of T and X. The big G is deterministic, yeah. Yeah, it's just a function of X of T. And now for option prices, often, we are looking to evaluate these conditional expectations, right? We saw that when we did Black-Scholes. This is under the risk neutral measure, but we are looking to evaluate these kind of conditional expectations. So now, this is no longer a martingale. This CTX, if I were to look at expected value of e to power r, should be minus here actually. Yeah, typos. All right. Minus r, t minus t, g of xt, given ft. Then this is going to be ct of xt. Right? But is ct of xt a martingale? We just used the fact that ct of xt was a martingale earlier. But now, is it still a martingale?
Yes, it's a conditional expectation.
It's a conditional expectation, but not of a single random variable. Well, you still have this constant inside, which depends upon small t. So what you can say is, this is not a martingale, but this guy is. The discounted guy is a martingale. And this idea will generalize.
Big T minus the martingale. No, within the martingale.
So big T can remain, right? It's just a constant. Big T can just come outside, but this quantity here is going to be a martingale. Okay, it's a conditional expectation of a single random variable. So now this quantity's Ito's representation, the drift term has to be 0. Right now it's not. Right now I've kept it 50. No, even if it was, everything will work out. Yeah. We'll do that in a moment. We'll do that in the next class, I guess. Yeah.
But we've done the same thing earlier, right?
We've not done we'll say that it's a martingale, we'll find the drift term, we'll identify the PD.
And now it is.
That's true. That we've done. That we've done. We will be generalized beyond it are being deterministic. So we'll be able to get the same logic to work here. In any case, so this guy is now apply Feynman-Clark formula to this guy right here, and then you get the associated PD. Let me just quickly kind of try and cover this thing so that next time we can cover more material. So risky in the Black-Scholes setting, we have this. So I'm just doing everything now in the Black-Scholes setting. So we have this underlying process, physical process based on physical data. Under change of measure, we've identified this risk neutral. Under risk neutral measure, we found this process, right? And then this is the option that we want to price, right? We had come up with this expression earlier, right? And then this guy is a martingale. So now we'll apply Ito's lemma to e to the power minus RTC. I'm just applying Ito's lemma to this guy right here. And that's minus R e to the power minus RT dt into C and e to the power minus RT into DC, right? That's minus R e to the power minus RT C dt, and then dCt is just this quantity right here by, again, Ito's lemma. Now I'm going to just, first was just, just Ito's lemma applied to two Ito processes, product rule. It's just a product rule, yeah. Right. And now I'm just going to put all the dt terms together. I get this quantity right here. This has to be 0. And that gives me my Black-Scholes equation. So that's the derivation of the Black-Scholes equation, basically. Okay. Basically, Black-Scholes equation tells you that the option price is a conditional expectation, and the conditional expectations satisfy a PDE. Okay. So now all of this we are going to, let me just take 1 more minute. Yeah, like I have 2 more minutes. So this you can, we'll also quickly revise maybe next time. Maybe we won't because we've done this enough. But the way we are going with now is now we are going to look at interest rate models. See, as interesting as equity, call options, put options look like, so that's how it all started. We're trying to do stock options. They form a small universe of option theory. Maybe not in India, by the way. In India, options have become big, and these are all kind of on indexes. But that's still not a stock price. But what's big in the world market are more these interest rate options, like swaps, swaptions. You have like caplets, which says if the interest rate exceeds certain quantity, then you get a payoff. Interest rate is 5%. If it exceeds 7%, you get a payoff. But these are now not for 3 months. The horizon is much larger, maybe 5 years or 3 years or something. And then you have floorlets. If it goes below certain points, then you get a payoff. And you have options on, you have bond prices and you have options on bond prices. And because the point is, interest rate options, generally, the kind of market you have in mind is long-term loans. Like housing loans are 30-year long. Many corporate loans are also of a much longer duration. Bonds have, maturity 10 years later, 5 years later. So you want to price those kinds of instruments. So what you do is you assume that the short rate, instantaneous rate, imagine that the rate that you're getting, say, for a 1 week's investment. So that you assume is, right now it's fixed, but overall it's varying with time. As a function of time, as weeks and weeks go by, it's varying. So it satisfies some stochastic differential equation. Okay? So that's what we are going to assume. It satisfies some differential equation. And often, as I mentioned last time, the way to use this theory is you assume that no arbitrage principle holds. So you assume that there's a risk neutral measure under which the short rate process follows this differential equation. You assume that that's the case. This is parametric. We'll talk about this parametric in some sense. And we say, okay, all our popular securities should have a price using this short rate formula. So I'll choose the parameters to match those prices. So that's how I come up with those prices. So assume risk neutral measure exists and has a parametric form. Estimate parameters using existing vanilla liquid options or securities. and then price other more bespoke or exotic options using this model. So that's the methodology consistently used for pricing things. So we'll talk more about this later. Okay? And this has gone in a major way. There was this was some of the best minds in the world nowadays. They go into machine learning. Like in every field, everybody's going to machine learning. In the early 2000s, late 90s, that was for financial mathematics. So many interesting developments happen. I'll just give you a flavor of some of these things in the next few lectures. What's that? Well, in the interest rate settings, I'll just tell you what that means. I mean, not even vanilla options, even bond prices. So if I'm assuming that my short rate satisfies this parametric equation, I'll choose my parameters in such a way that I match the bond prices that I see. So not even options, yeah. Okay. All right. Yeah, we have a quiz Friday. Yeah, we have a quiz on Friday.